Hi, everyone. I hope you are able to hear me clearly and
Hello,
and,
everyone.
and meet Venkat. So wonderful to have all of you in this discussion. So before we start, I'll just give you a brief background about myself, and then I'll ask Venkat to introduce. So first of all, welcome to this session on the scalable machine learning. Though the topic is scalable, but it's going to be more about ML ops, more about the psychological shift between the traditional way of thinking and the machine learning way of thinking. The challenges that you face when you are dealing with machine learning project, and the challenges that you have not foreseen if you were into non-machine learning environment. So basically this session is going to be a brief overview, a fun overview, and that's how it's going to go. And I'll be asking questions on your behalf to Venkat. And also meet Venkat. Venkat is a staff engineer at Google Search, and that is something wonderful to have. To interact with Venkat today as part of this webinar, and you will get to know the real perspective of how the machine learning happens at Google, as well as the nuances of machine learning. So, a brief about myself. I am Sandeep Giri, founder of CloudxLab, and there'll be Abhinav, who is a co-founder of CloudxLab, who will be joining us soon. And it's going to be an interactive session between me, Venkat, and Abhinav. Abhinav and I will be proxy for all of your questions, and we'll be asking those questions along with our own questions to Venkat. All right, over to you, Venkat. Please feel free to introduce yourself and yeah, what your
Hello, folks. My name is Venkat Karun. I work on Google Search ranking, and I've been at Google for slightly more than 12 years. I worked on various parts of the Google stack, but I tried my work in the homepage team. I worked several years in Mountain View, California, before I moved to Brazil 7 years ago. And we have a search engineering team based out of this office, and I work there. Well, as in me and Sandeep, we go back to 2004. And like in a certain sense, Sandeep was the senior when I joined DE Shaw, and the senior who taught us SQL injection attacks and
so
who
the
called out. Yes.
yeah,
So I
there
think
was
I'm
this
so happy to.
there was this workshop that I conducted called secure programming, and yeah, that was like a very interesting one, and that's how I got to know everyone. Okay, go ahead.
So I'm super happy to be associated with CloudxLab and the AI Siri program. And today I hope to give a sort of fun presentation about the world of scalable machine learning. As in my perspective is, if I think I look at it from a Hugging Face prerequisite, which I'll go into it in detail. But with that, let me just share my screen and start.
All right.
All right, presentation mode. So I hope everyone can see this clearly. My audio is good. Well, so let's start. So all of us, I think we've got to think of the paradigm of deep code, right? As in, so what exactly is deep code? So let's, we both introduced ourselves, so I'm going to skip that. So let me start with the prerequisite for a Hugging Face experience, like shout out to Hugging Face for the NLP work, that you understand technology and software development. If you grok the fundamentals of machine learning, It's going to be a slightly tighter hug. And well, if you have an applied knowledge of a framework such as TensorFlow, PyTorch, or Spark, I hope it's a bear hug that we get. Now let's I'm a huge fan of XKCD, and I'm gonna use XKCD liberally because behind the humor is a whole lot of philosophy, right? So today, when I'm going to start with the perspective of comparing machine learning versus traditional software, and so when I talk about machine learning, right, the neural network is not an engineer labeling by hand and saying, yes, I've trained a neural network to sort out label photos into categories. So when I'm talking about neural networks, I'm really talking about convolutional or recurrent neural networks. So in traditional software, right, as in, I think this is sort of like a separation of concerns. Data should not influence code. We've got the front end, we've got the back end, we've got the MVC pattern, we've got modularity, we've got design patterns separating to the finest level from the macro scale to the micro scale. Yep, so we separate all the concerns, and that's a iron creed. But, well, in machine learning, your data influences the code. What does separation of concerns actually mean in this case?
Yeah,
there's no separation of concerns.
I remember my days long back when I was teaching secure programming as part of my joy. I had an immense focus in my presentation about separating code from data, separating code from data. And now I look at the same thing that I was teaching and I say to myself that yes, I was wrong in some ways, and this is the time that is that realization. Okay, go ahead. Yeah.
Indeed, Sandeep. I mean, I fell into that same Alice in Wonderland scenario many times. I think so.
So those who are new to it, I'll explain to you. So usually, when you are writing secure code or the software practice, we tend to keep data in database or file system and keep it separate from the code. And that's something, the code data should not become instruction. But when you think about machine learning, what's happening is that lots of data combined together leads to set of instructions, right? Because we are learning the rules from the data. Therefore, um, logic and the data are inseparable to a very large extent in case of machine learning. All right, go ahead.
Excellent perspective, Sandeep. Thank you for that. So let's actually take a look at data dependencies dominate code dependencies, and Sandeep's made it very clear, right? Well, so what sort of data dependencies? You have unstable data dependencies, right? Data constantly changes over time. I mean, let me give you a classic example that everyone's going through, the COVID cases, right? I mean, let's just take of that as a canonical example. And underutilized data dependencies, like feature bit rot is a real concern. I mean, somebody added a feature 5 years ago. I mean, do we really go back and clean it or check whether it's valid? Well, I mean, I think it's more if you are very diligent about technical debt, then it's very likely that it's just rotting in the system. So, I mean, when we talk about this, I think the cognitive coder explains this brilliantly, like the 80-20 data science dilemma. That means like most data scientists spend only 20% of their time on actual data analysis and 80% of their time like finding, cleaning, reorganizing, right? Dealing with the under-specified, the over-specified, like, essentially that's machine learning data work in a gist. Now let's go to the other aspect of my another favorite XKCD about the pile.
I would like to say that the previous screen, I actually feel it's like 80, 15, and 5. 80% of time figuring out where is the data, 15% of the time figuring out how to analyze data and doing the analysis, and like 5% time is fine tuning that model and deploy, doing other things. Okay. Anyway, yeah, go ahead.
Yeah, bang on. And actually, it should be the other way around, and maybe in a certain sense, right? So you said that, like, maybe that 5% is the key thing, right? Like,
Yeah.
yeah.
Yeah. Okay.
Cool. So let's actually go into now the other XK thing. All right, this is your machine learning system. Yep. You pour your data. There's a big pile of linear algebra. You collect the answers on the side. What if the answers are wrong? Well, you just stir the pile until they start looking right.
Yeah.
Unfortunately, this is not just
Yes.
wishful thinking, right? Because neural networks are a black box. What does that
Yeah.
really mean?
Yeah.
Well, and we actually have a famous theory called information bottleneck. The image on the right is symbolic of the information bottleneck approach to debugging the black box. But
Can
each
I?
time you leverage that, that's where you go and
Okay.
too many neurons.
Yes.
That's
Yes.
essentially the state you run into.
Can I just for those who are new to this? So when we talk about explainability, it is essentially, can I explain how did my model recognize the face? How did my model did what it did, right? Just like people say, "Oh, my heart says so," and that's how I feel. That's essentially meaning that it's not explainable, right? So explainability is essentially by looking at the model that it generated after training and while you're doing prediction, can we explain how did it do the prediction? The the trade-off is there. There are simpler models which are explainable, such as decision tree or linear regression or others, while the complex models such as random forest, they start becoming unexplainable. Similarly, it's very hard to explain a neural network. A neural network is fairly unexplainable, though there are lots of work that are going on explainability, but still the explainability is very low in case of neural network as compared to the other ones. Okay. Yeah.
Brilliant. Thank you, Sandeep, for taking the
Okay.
gist, because that was very important when we come to this. So Jeff Hinton, I mean, if it's quite famous. I mean, if you are into AI, okay, let's consider this question. Suppose you have cancer, and you have to choose between a black box AI surgeon that cannot explain how it works, but has a 90% cure rate, and a human surgeon with an 80% cure rate. Do you want the AI surgeon to be illegal? What do you think people will trust in this scenario? Like the YouTube universe, anyone chime in? Who would you trust here?
I would still go with 80% cure rate. I'm sorry, but
You would
yeah.
go with 80% cure rate?
Yeah.
Well, the Twitterverse doesn't agree with you,
Okay.
right? So,
Okay. Okay.
so I think this again goes back to the key gist, right? As in, why is explainability important? Because in a certain sense, sometimes people like just assume AI just works, and then you got a black box, right? People haven't really checked if it works, right? As in, let's consider the skin cancer detection problem, right? As in, can you really explain a false negative, a case which is actually terrible for that scenario? And if that isn't like explainable, then your model fails, right? Doesn't you are failing the patient in a certain sense.
I'll give a similar analogy. So if there are two doctors, one has a 90% accuracy and other has 80% accuracy. Both are human surgeon. Okay. The first one just does it and doesn't explain to you. And he says that here are the pills, eat them and go home. And the second one who says that these are the pills. This first one is for this, second one is for this, third one is for this, and uh, and you have this disease, and this is why I'm giving you the pills. So I would like to go with a doctor who gives me the pills with an explanation as compared to another doctor who doesn't give explanation. Okay, sorry to get into that, but yeah. So that's my
I
take on
think
it.
it's a very interesting debate, right? Because Twitter was right, like that's and Jeff Hinton probably has like thousands of followers, right? So that's like an indication. But cool. Let's now go back to uh, well, XKCD 1838. Now this again, like is starting with humor, but goes to a very serious problem, right? Okay, so you have the first person. I made a fully automated pipeline that collects and processes all the information we need. It's a, and then you've got the person who really understands the world as it is. So she comes and says, "Well, is it a giant house of cards built from random scripts that'll completely collapse the moment any input does something weird?" Well, it might not be. Oh, just collapsed. I can't patch it. Well, so that in a certain sense explains the testing aspects of machine learning, right? I mean, if you are in machine learning, if you are in traditional software, unit tests, regression tests, integration tests, smoke tests, black box tests, you will be. I mean, you probably would have done this in your software engineering course in a certain sense, studied this, right? Now, it's an essential part of your development life cycle. But in machine learning, tests take each step takes you further away from the goal, right? I mean, if you conduct a poll, I'm sure most people will, oh, wait, you actually have tests for your machine learning system? Oh, that's cool. But why is this important, right? I mean, we shouldn't consider this. So the analogy of yak shaving, for those who aren't aware with this, is it's like, work that superficially looks like okay, but then it's actually like you take a small Gillette razor and try shaving a Tibetan yak, right? That's
Yeah.
probably going to take like maybe a month, if I'm not sure how long, but that's essentially the gist of it. Uh, if we go into the real problems, testing concerns, right? Like
So
remember, both myself and Sandeep, we spoke about data, right? I think
can
data. Yes,
I
yes, Sandeep, please.
so I remember in 2012 at InMovie, the we were building the recommendation engine, and this guy from QA comes and says, "Hey, is there something called testing in case of machine learning model?" Right? And then I said, yes, of course there's a testing. And then how do you test something that is we are predicting in the future, right? I said that the way you test anything like based on the existing one. So what we had to do was we had to design a small kind of a talk for them, like explaining how machine learning works and things like that. And then they were up and running with the testing. So the testing has to be the integral part of the machine learning, and it worked out well. Okay, please go ahead. This is
Excellent. Thank you, Sandeep, for that, real world story.
yeah.
So I think data is important, right? So data correctness and usefulness, we need to test for that. We need to test if the underlying data distribution has changed for a feature or random variable. Now, like, let's say you make a prediction based on most of your values falling between the 50th to 75th quartile in a certain sense. But all of a sudden, all those values shift to the 25th to 50th quartile. Then, like, your fundamental assumptions break. Now, can we actually quantify the delta that I spoke about, right? Where your variable has changed and you need to find out if it has shifted. Now, CI/CD, right? Continuous integration, continuous deployment. I mean, that's, I'm not going to go too much into it, but it's like, yes, I want to release my code frequently, and it's healthy to release my code with a pipeline that is robust enough to detect regressions in my machine learning models. But is your CI/CD pipeline actually testing for distribution shifts in your features or random variables? Can you disambiguate between the good eggs and the rotten eggs in your basket, right? As in, like I said, the rotten eggs, the data, the pile falling off, the XKCD thing, that one thing that collapses your stack of cards, right? So that's one thing. And do you have adversarial testing infrastructure in place? And with, like, adversarial testing, well, what does that mean? Let's go into this in, like, I would call it a diversion, but I think it's important, right? So let's consider a tweet on the first column on the left, right? And using Trickster, which is like, I have a typo there. It's actually attacking machine learning, not attaching machine learning. I need to correct that. But it takes the model, what it does is like sorry and meritless, accidentally, incidentally, name, figure, relationship, status, kinship, position, beautiful mind, beautiful thinker, huge heart, huge spunk. How is it, like, actual transposition done? Using WordNet, synonyms of, yes, Sandeep.
So it is basically, there are like, we are trying to predict the confidence, whether it's a male or not male, right? Given the text.
Exactly.
And so there is a original one. So sorry, friend, but unfortunately, the TARDIS cannot translate stupidity. The confidence for male is how much? Okay,
it went from 46 to 55, right?
I see.
Like, I think the key thing is not the content itself, but how much an adversarial attack can cause a massive confidence change for a key indice like agenda, right?
Mm-hmm.
A very simple perturbation of your data using WordNet synonyms, that's all. Randomly pick words, synonymize with WordNet, like, nouns or adjectives or some similar thing, and look at that. Mind and thinker. Oh, the man is so much more of a thinker because of that perception.
I see.
Right?
I see.
And just when you move from relationship to kinship, also women are more concerned about relationships and men are more concerned about kinships.
Interesting. So it seems like there are words in the model. The model is trying to predict based on a couple of words, such as thinker. Suddenly the word thinker comes and it becomes like as if it's being told about the male as compared to earlier. Interesting. Very interesting.
Yes.
Very interesting. Okay.
Thank you, Sandeep. Can I continue any more?
Yes, please. Yes,
perspectives
please. It is very, very interesting to note that a slight bit of attack on the text or just modify it to the random thing could lead to very weird results, and that's a very, very interesting perspective of testing the model. Yes, very, very interesting.
I love the Trickster library. I personally use it at work. In a certain sense, and I mean, are adversarial attacks testing common? I don't think so. I think it's a very niche probably very few teams do it and as a part of their daily workflow, right? There might be performance tests, right?
So
or latency tests. Yes.
This tool can make it possible to attack and curate an attack, adversarial attack on you.
Yes.
Okay, interesting.
Yes, and it's got various different models, various things. I think, like so I would I think like perhaps maybe a session when we do a advanced thing on this might be cool.
Okay, wonderful.
All right, now let's actually consider the third aspect of machine learning versus traditional software, which is the computational aspect, right? So you've got your MNIST, right? The typical, the holy grail of image classification, right? You've got 100 image tensors, or 100 images, one flattened per line, right? And you are essentially doing weight multiplication, right? And WX plus B, right? Just for this calculation. Now you see what is that FLOPS, right? That's on fire there. Floating point operations per second, right? As in, the key difference between machine learning code and your regular web servers that fetch something from MongoDB, or your create, read, update, delete databases, or your queue systems, or even your distributed systems, or your big tables, or your relational databases, is that, like, the compute intensity of machine learning. And what do I mean? And let's actually take a look at some, like, this in a little more, take a step back, and on the left, right, you have 40 years of CPU trend data, right, from NVIDIA. And on the right, you see the exponential growth in the training of artificial intelligence programs, right? So you can see, right, as in, what is the key y-axis? Petaflops, right? Peta, floating point operations per second. Look at where alpha 0 and alpha go are. 10,000 petaflops per day. That's a training overhead of AlphaGo, right? As in, like, a sequence to sequence is significant, and that's like, everybody trains it. Like, look at visualizing and convents, right? So ResNet is here, exception is here. So I mean, it's not like, okay, it's not like AlphaGo and AlphaZero is what we train every day, but the ones we train every day are also expensive, right? So now the same perspective, right? Let's take a look at from a little more detail, right? The 40 years, what has happened over the 40 years, right? So we can see that the number of logical cores has increased, but the typical power consumption in wattage has plateaued. The frequency in megahertz has plateaued. Single-threaded performance has plateaued. And transistors, even though they're sort of increasing, right? I mean, it's still like, it's not linear, it's sort of becoming sublinear in a certain sense, right? But at the same time, GPU computing performance, they predict, like, 1000x improvement by 2025. But a graphic processing unit is a fundamentally different beast, right? As in, like, your von Neumann model of computing does not apply to that. Like, you've got to wrap your head around different abstractions. And do you actually really use GPUs for deployment? I mean, it's mostly for training, right? As in, and even if you use GPUs, like, they're super expensive, right? As in, I think the key thing is, like, one needs to consider that, like, okay, you're paying the cost, right? But the single-threaded performance has tapered off. Your serving systems are mostly going to be the CPU serving systems. So hence, efficiency and latency matters a lot. But let's go into the next slide. Now, why machine learning versus traditional software? Now, MLPerf is the standard, like, I mean, this is the canonical industry-wide performance benchmark that I'm talking about here. Like, SIMD, right? Like, a single instruction operating on multiple data, right? So machine learning is fundamentally dealing with, like, floating point operations, right? Let's talk about WX plus B is actually a single instruction in the Intel math kernel library in sort of like the hardware thingy. So like the single instruction or advanced vector extensions, the size of the vectors in your machine registers, what does that mean? Like you might have 64-bit vectors, 32, 64, 128, 256. Okay, let's take that thing. If you put like obviously 256-bit vector can store more floating points, right? 464-bit floating point values, right? So consider that, like, the larger the vector size, the faster it gets, but also they are fundamentally changing like the sub-vector operations, right? And on the right, like, I think it's very, very interesting. All right. These are actual models. Now, the one API deep neural network library, actually, if you look at the title of the slide, it's Intel Math Kernel Library. But Intel has become a part of the one API effort, and this library is now known as the one API deep neural network library. So Intel has come out with native hardware level abstractions for your machine learning operations, for your convolutions, for your dropout, for very many operations. And let's talk about throughput. What is throughput? The number of operations that you can perform per second. So let's say you're doing image classification, the number of images that you can classify per second, right? With the Intel Math Kernel Library optimizations, it is 2.26 times faster than in a vanilla setup, right? All the Docker containers that you run, Amazon Sage, AWS, any of the systems that you get off the cloud, they are not compiled with Intel MKL. But if you compile with Intel MKL, this is the speed up that you get. Now we are in the, I would say, a Cambrian explosion of transformers in a certain sense, right? Now for transformers, it's even more significant, right? And like we are entering a world of large language models. So like all of our data science courses, right? And like it's heavily focused on like the mathematics of machine learning, the implementation of machine learning, the analysis, but the hardware, vector instructions. Do we really go in that deep, right? As in how? Yeah. So I think that's one fundamental facet that.
One of the things that I see there is a gap in most of the education, and that it's very important that you brought it up. That when we are training our models, can we take the GPU into consideration? Similarly, while we are launching our models, can we take the same, the hardware into consideration, right? And we see there is a humongous gap. Keeping that gap in mind, I'm launching this this course called Accelerators on GPU by Professor Sparsh Mittal. His PhD is in hardware. His PhD is designing these accelerator for the hardware, and right, he's the basically that's his research, and we are launching that one. So probably that will help, or the MLR, the course that we are planning to gather, me and Venkat, the next course on scalable machine learning, all of these parts we are going to cover in more details, and that will help people to do it. Because I remember recently discussing with this guy who is trying to do something on the physical hardware at the runtime, and he says that we are not able to utilize the hardware's, the capability in real time because we did not know how to divide a logic onto multiple GPUs. And that's something that is next generation of computing that we need to learn. Okay. There is, Pankaj, there is a question.
Fantastic, Sandeep.
Okay. There is a question about by somebody. The question is the tool that you talked for adversarial testing, is it more like test augmentation or during testing in addition to the regular data that's already there?
It is exactly that, right? As in, it is augmenting your data that is a part of your test suite in a certain sense, morphing it, changing its characteristics. So yes, you answered your question.
Okay.
Cool. I think, like, the fact that Sandeep brought up this, right? I'm gonna go to MLPerf, right? And this table, like, let's see all of the tasks, right? Vision and speech and language and commerce. We've taken some canonical examples, right? For vision, we've got image classification, we've got object detection, and we've got medical image segmentation. For speech, we've got speech to text, right? With and the data sets are, like, the canonical ones. Language, we use BERT with Squad, which is the Stanford question answering data set. And so commerce, the 1 terabyte click logs data set, like, look at the, yes, Sandeep.
Which hardware is
it's I mean, this is actually the latency constraint, Sandeep. If you actually click on the benchmark, they show, yes, this is not the benchmarks itself. The benchmark is, clicking on that link, I think maybe we share it. It's amazing. It shows, like, it's, I don't know, maybe 10,000 rows in a spreadsheet.
Okay, got it. Okay.
But I think the key thing is the constraint, right? You want your image classification to run within 15 milliseconds. Your object detection to run within 100 milliseconds. 1 second for speech, 130 milliseconds for language, and 30 milliseconds for commerce. Now, where do these numbers come from? And I'm going to go into that. Now, responsiveness matters.
As part of this course, we are going to help the people how to deploy your models such that you can reach this kind of constraints, the one that was mentioned by Venkat. And that's one of the good thing that he has put in, that this is something that should, like, we were deploying the face recognition system, and I saw this pitch by somebody. I was sitting in that, and I asked, like, how much does it take to recognize faces? He says it takes 15 seconds. I said, can you show it to me? 15 milliseconds, he told me. I said, can you show me? Where is it taking 15 milliseconds? And the way he had deployed the entire pipeline was that every image was taking more than a second. Okay. And that told me that, fine, he's able to use the model out of the box from the internet, but he definitely needs a lot of knowledge on how to deploy things so that it can be, 15 milliseconds. And the same thing we did in case of, like, in CloudxLab, we were trying to reduce the latency and trying to bring it to 15 milliseconds on the face recognition. It took us a decent amount of engineering. And that's something I find it very much, what do you say, very much missing in the industry, that everybody talks about the same course, same thing. Everybody talks about training it, but nobody talks about, how do you deploy it such that you can meet these constraints that Venkat mentioned just now. So wonderful. This is something that is very great for the users. And yeah, thank you so much for bringing it. Go ahead.
Excellent. Thank you, Sandeep. So, as we can see, right, as in the average user has no patience for a page that takes too long to load, and justifiably so. And in the internet age, attention span has even reduced further. So maybe seconds are also a stretch. So Why does responsiveness matter? Like Walmart has found that conversion rates decline sharply as the latency climbs from 1 second to 4 seconds, right?
Yeah, yeah. At Amazon, we
Amazon
have, yeah, I was in this team, okay, and
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 Sandeep,
every
please take over.
millisecond saving turned into money. Okay. Therefore, our entire focus was on how can we bring the latency down. And the numbers were so sharp, you cannot contend with it. You cannot say, oh, a person saw the slow website, he might come back later. No. The truth is you lose revenue on latency. As simple as that. Wonderful. This is very good.
Perfect. And Akamai, right? I mean, they essentially are the backbone of the internet. And a 1 second delay in page response, 7% reduction in conversions. Again, these are like drastic metrics, right? So latency first, and machine learning is latency sensitive. So this needs to be a first principle in ML practitioners, in my opinion. All right. So talking about latency, let's actually take a step back and think of how do users perceive latency. Now, users are exceptionally good at tracking motion, right? And they hate it when animations aren't smooth. So users perceive animations as long as it's 60 frames per second. I mean, the gaming nerds, I think you this is probably too slow for you, but the 60 millisecond per frame, right? That's the time it takes for the browser to paint the new frame to the screen, leaving an app about 10 milliseconds to produce the frame. So you have 10 milliseconds to do your whatever image classification approach that your model needs to do. You need to respond to user actions within 100 milliseconds for them to feel like it's natural. 100 to 300 milliseconds, they start feeling it slightly. 300 to 1000, okay, they'll wait, 1000 or more, goodbye, essentially, in a certain sense. So I think with that, I am gonna pause for a bit, right? Because we are gonna start a segue into the core tenets that we're gonna talk about, like the life of a machine learning engineer, the life of what we call with the colab pipeline, right? The colab world that we all love and we start with. So before I jump into this, I want to see if the audience has any questions, because I'm changing focus from the traditional software versus ML and going deeper now into real architecture and systems design.
Right. So I think this is something that is very interesting, that we so far talked about the challenges in usual machine learning, and the most of the courses that I have seen mostly focus on theoretical aspect of modeling and so on. But what I see from this discussion and the key takeaways are something to do with testing, deploying, and gathering data, and choosing the different kind of models. So I think this is something that is going to be unique in this course. That, I mean, I think people are calling this as ML ops, isn't it? These days, people call it ML ops. So and okay.
Definitely.
And in upcoming course, that's our plan, that we will incorporate, right? I mean, Venkat will be incorporating the real
Yes, I'll be working very
challenge,
closely with Sandeep on this.
the real challenges that people face in deploying the model in practice, in real life, and how do you build a whole process around making your model deployment perfect, like without any without any delay and without any latency gap, and make it run. So those are the main tenets of the course that we are planning together. And I'm sure that this would help companies a lot. So in my personal perspective, I'll be very honest with you. Okay, in one of the in one of the system that I designed long back in 2012, I built this recommendation engine on a large scale system. And our system was taking 4 GB of memory. Okay. And we thought that 4 GB is okay while running. Our model was taking 4 GB. But when we put this model in production, the production guy said you cannot say take 4 GB of memory because this is an expensive operation. You can at most have 200 megabytes of memory. Okay. So at this point of time, I felt extremely bad about this. It felt as if, I mean, who talks about 200 megabyte, right? Like we are only asking for 4 GB, but if you look at the perspective of the engineer who was handling the DevOps, they said that it's a ad serving engine, and ad serving engine, if they start giving 4 GB to each, even like 200 GB of RAM will not be sufficient. And that was very, very important. And that was a big learning. So we went back to the desk, thought about how can we bring down the memory constraints. And we were able to do it, but it required a decent amount of thinking through. And most of the engineers I found gave up at that point of time, saying, oh, this is like the world is unfair and this is not what I signed up for, this, that. And we ended up with that mindset. I mean, most of the engineers give up on that. And this is where I feel that the perspective that you brought up is going to help lots of engineers in building and deploying real stuff in the world.
Thank you, Sandeep, for that, amazing perspective on MLOps and introduction to MLOps. So let's consider the small colab pipeline world, right? So you have your problem. It's all hyper localized in a nice circle.
Can I intervene one?
Yes, thank you, Sandeep. Thank you so much for the amazing insight and perspective.
There's a quick question from somebody. Question is, it is a performance optimization for machine learning model. The Intel API kit that you talked about, can it be called directly from the Python code? I think so, right? The question is that the Intel API kit that you talked about, can it be called directly from the Python code? It is a Python API, isn't it?
Yes, actually, I put a reference out there. It's actually NumPy, SciPy with Intel and KL. So that's piped up there for you. I mean, it's fundamentally enhanced for Python. They've got various versions of Python wheels with Intel MKL compiled optimization. So I recommend you actually use the Intel Python packages if you can, right? For NumPy or SciPy if possible.
Okay, wonderful.
Great question, Kalyan Robin.
Go ahead.
All right, so let's see. Keras, Flask, and Docker, right? That's a canonical small data pipeline world. Like you build your model, you push it from the colab, you build a small serving container for that. And delving into your flow, right? As in the colab pipeline, right? As in, let's take a look. Okay, there's a model development and there's the prediction with your trained model. So the model development, let's start from left to right. You get the data, you clean it based on some a priori knowledge, you define the features, you do your transformations, you select the model, you might do some parameters to optimize the model, right? And you define scoring metrics and calculate the accuracy of whatever you define, and you rinse and repeat many times, right? And in the previous slide, I was showing essentially the rinse and repeat stuff. And once you rinse and repeat, this persistence is typically a file system, right? Some either a pickle file or an H5 file or a Parquet artifact or some other artifact, right? And then you This is your real-time flow. You get unseen data, you do your cleaning, you transform the raw data into your feature representation, which is vectors or tensors needed for your model. You make the prediction and you pass the results, right? All good. Is it? Well, but as the data and its dependencies grow, right? Actually, this sheep is Barack. I mean, named after Barack Obama. It's quite famous in Australia. So it's not like it's a celebrity sheep right there. As the number of models grow, I mean, this is the Netflix world, right? And look at the number of use cases and what all Netflix uses machine learning for. Screenplay analysis using NLP, machine translation, fraud detection, content tagging, word of mouth effects, CDN caching, a completely different domain space because Netflix streams so much data that they need to worry about machine learning at the edge, tweet clustering, prediction of network quality, classified tickets, marketing systems, right? So you see the breadth and the depth, you see the models, you see everything, right? Now let's take and the frameworks go, right? I mean, it's not like everyone likes the same framework, right? And we have several brilliant frameworks, right? I mean, TensorFlow is good, PyTorch is good, Piano is good, NumPy is good, Spark, NLTK, everything. I mean, everything I love here. I mean, probably TensorFlow is the most difficult to use among this, right? In a certain
and there are different versions of each.
Exactly. So I mean, Sandeep's just nailed the thing, right? As in, like you have switching between 1 and 2 in this is a nightmare, right? So let's just or 2 and 3 or anything, right? So they liberally do major minor version updates whenever they feel like, and always incompatible. Backwards compatibility is not a concern in API development. Unfortunately, I don't know why, but that's a problem. Next look, and the framework of choice crusades commence, right? I mean, the C++ versus Java, well, you have the PyTorch versus TensorFlow, fast AI, lightning, auto hugging face, everything is about fast these days, right? Like, lightning, PyTorch, lightning. So it's framework wars, but so then your conventional, your serving stack, you need to think more, right? Your conventional approach doesn't work anymore. You need to split things into a more nuanced and refined world. Your serving stack becomes infinitely more complicated because your feature engineering is split into training, validation, test worlds. You have a building model world. Then you test the models, you tune the parameters, and then you compare the results, right? But as the complexity evolves, right, so should the infrastructure, right? And this is the key tenet that I'm going to talk about, right? This middle layer bridge, right? This is MLOps in a gist. Model and data versioning done brilliantly well, right? So that you can go back in time, debug your models, debug what data versions cause these models queues, do the combinatorial splits of different models, different data versions, be able to do A/B tests comparing different model versions, be able to do A/B tests comparing different versions of your features. So that's then deployment orchestration, right? I mean, you got to support all your camps, right? Your PyTorch, scikit-learn, Keras, MXNet, the Spark world. So I think this middle layer, the bridge, leads to what we consider like, the ideal machine learning pipeline, right?
We got
the model development on the top, the model serving, and then the plug, the glue, right? The engine in a certain sense, the V12, the Colombo Ferrari V12, that's MLOps, right? So, with that.
A quick question. So yes, can you go back to the previous screen? Previous one. Yeah, this one. So question is that as the gap between production and the desktop separate is wider now. There's this MLOps, model versioning. So do you think the syndrome also increases? Like it works on my desktop, but it's your problem that it doesn't work in the production. Does that happen too often at Google and elsewhere? Right? There's this thing like, oh, it works on my desktop. Yeah.
Definitely. Definitely. It works in my colab. But that's it.
It works in my collab, yeah. There is a good question. Question is, it may be a naive question. I'm switching from Java development to data science. Usually we deploy web application in web application server. Where do we deploy a machine learning model? Okay. Do you want to answer this question, Venkat?
Sandeep, you see again, like I will answer from one perspective, but you bring your Spark perspective in, right? So, okay, you're switching from Java development to data science, but Stanford has a core NLP Java library. You have deep neural network libraries in Java. You have Spark ML lib, right? So you can take your models and build something like a drop wizard serving stack for your Java server and continue with Java, right? There's no need. I mean, so like I said, yes, please go ahead.
Okay, so I like to add there. So yes, wonderfully, as Venkat said, that you can actually deploy. There are so many Java libraries, and model is nothing but bunch of numbers, right? Model, whether any model, is essentially bunch of numbers, whether it's a decision tree, random forest, SVM, linear regression, logical regression, or neural network. It's bunch of numbers, and usually those bunch of numbers, no matter which programming language you trained them, right, will generate these bunch of numbers called model. And then you can load it using any programming language and framework as mentioned. But very important point that we would bring up in this course as well is that it is wiser to launch independent model as a microservice, because the scaling pattern for both is different. Your web server would not require that much GPU or would not require that much CPU, but a model would require more CPU, more, a consistent RAM. And therefore, since the scaling pattern, the usage pattern is different, so it's better to just break it up the monolith application into the smaller microservices. One microservice, as Venkat was saying, that if you take a case of Netflix, there are so many use cases of machine learning model as of today. And you basically, the way they do is they keep separate service for each of them, probably inside a Docker or something, right? And deploy it there. So, and therefore you can independently scale them, you can manage them independently, and also you don't get into this version hell of various between like conflict of programming languages, conflict of libraries. You might install Python 3 on production and so on, and there is like always this consistent conflict of versions and things like that. So it's better to break it down into parts. Did I make sense, Venkat?
Perfectly, sir. Now, I'm going to go to Michelangelo, right? That is Pieta, one of Michelangelo's most famous sculptures, right? So let's take a look, right? As in, that looks pretty impressive. So we've got like get data, train models, eval models, deploy, predict, and monitor. So it covers the entire gamut that we've spoken about right now, right? So let's go into
Michelangelo is essentially bunch of tools. Is it like a virtual machine that people can download, or is it like?
No, it's Uber's internal system, right? It's completely their in-house internal system. But they have a public blog post talking about how they do it,
Okay.
So let's start Uber obviously with the use case, right? As in, so let's go with the Uber Eats, predicting estimated meal delivery time, right? So you've got to, it's a complex multi-stage process where you have to recalculate at every step, right? The first is the order is placed by the customer, sent to the restaurant. The restaurant acknowledges and prepares the order. Now, the time is gated on how busy the restaurant is and the complexity of the order, right? I mean, your gulab jamun versus a 10-course Michelin-starred meal is going to definitely take more time, as well as how busy it is, right? So, and the other thing is, like, your delivery partner should use the fastest route, which is essentially the traveling salesman problem in real time, right? So, how does actually Uber do this in a certain sense, right? So we've got to think about all the steps of the process, right? So let's start with managing data, right? So transactional and log. So we've got the offline data, right? And the online data scenario. So let's start with offline, right? So transactional and log data. So transactional data is like, your purchases, right? And then log would be like, a log, an audit log of where the delivery agent is and all of that, or in something else, right? As into an HDFS data, right? And I'm not going to talk about what HDFS, Spark, Hive. CloudxLab has amazing courses on all of these facets. So, please sign up because they have brilliant courses covering many of these facets. So, Spark and Hive SQL compute jobs, compute and publish features, right? So that's essentially here, right? To a feature store, right? And a shared feature store. Now, what is a shared feature store and why would you need a shared feature store? When you have so many teams building so many products, it's likely that there's going to be some commonality in the feature space that they use, right? So, you don't want to reinvent the wheel. DRY, don't repeat yourself, is one of the fundamental tenets of software engineering that we strongly adhere to. And the same thing goes for ML. And Uber's taken that principle and distilled it brilliantly with their shared feature store approach. And that's in Hive. All right. Yeah. Now, let's consider the online conundrum, right? Online models cannot access HDFS, right? So that's one problem. It's very difficult to compute features online. Average meal prep time, it's going to be slow. It's costly. You can't, the overhead of this is crazy, right? So what do? You do bulk pre-computation. That's one approach. You take batches, right? You take your historical features from HDFS and you push it into Cassandra. So that works for average meal preparation time over the last 7 days. Cool?
Wonderful.
But there's also near real-time compute, right? So where they actually publish data to Kafka, run SAMSA compute jobs that write to Cassandra. And note, you're logging it back to HDFS so that you can retrain with this data that your online process has collected, right? Again, machine learning, you need to continuously evolve. Now, what is this used for? Average meal preparation time over the last 1 hour, right? So again, I think the historical versus online near real time is totally explained by the week versus the scenario, right? Now that we've explained getting the data, right? The online and the offline scenarios. So we've got it into the Cassandra feature store or the Hive feature store. Now Uber has many different models, right? Like I said, they do large-scale distributed training of decision trees, linear and logistic regression models, unsupervised models such as k-means, time series models, deep neural networks, transformer variants. Anything that an AI team or even latest state-of-the-art that Uber's AI lab comes up with, right? So they essentially, right? When you have many things, what do you do in computer science? You create a configuration and a domain-specific language to make it easy to replicate that over and over again so that you can copy the configuration So Uber's actually created like, a model configuration. The type, oh, here I'm using a XGBoost, or there it's a random forest classifier, or there I'm using a DNN. Source reference for the data, feature expressions, right, where they've done it brilliantly, where their feature expressions are Scala functions. So you have the composability of higher level Scala functions to build your features dynamically. And it's also important that when you define a model configuration, you specify the requirements, right? Like the number of machines that you need, how much memory you expect that to consume, whether or not you expect to use GPUs. Now, I honestly think this should be automated. This should not be the job of a developer to specify this configuration, but like, that's just my perspective. All right. So after the model is trained, you've got your performance metrics, right? Accuracy, precision recall, the receiver operating characteristic curve, the precision recall curve, plus confusion matrices, and they combine it into a model evaluation report, right? And at the end of training, the model configuration, the learned parameters of the model from a hyperparameter search, and the evaluation report are saved back to a model repository for analysis and deployment, right? So this block is the Cassandra model repository. So not only is the data versioned properly in the high feature store, but the models are also versioned properly in the Cassandra model repository, right? So they've tackled the middle tier problem of data versioning and model versioning with this facade. Now, I said that like Michelangelo supports hyperparameter searches for all model types as well as partition models. Now, like, what are partition models?
Is it possible to take a break? Hello, can you hear me?
And this is like, where I'm going to not cover. Let's take a break.
Hi, Venkat. Yeah. So can we take a break of 10
Hi,
minutes?
can you hear me?
Yeah, I can hear you now.
Yes, please.
Can we take a break of 10 minutes and be back after 10 minutes?
Yes.
All right. So we'll take a break for 10 minutes and we'll come back at 9:18 p.m. IST. Okay. So break for 10 minutes and we'll be back by 9:18 p.m. IST. Hey guys, so by the time Venkat joins in, and by the time we start, all right. So I'm back.
Hello, folks. I'm back.
Okay, wonderful, wonderful. So this is actually going very well, and I'm actually this. Um, this is something that I'm also looking forward for, right? The things that you're talking about, and there are a few very insightful things I got to know. One was having a feature store in place is a very cool idea. So I remember in all my jobs, so one data scientist is working on X project and the other one is working on the Y project. And they both end up doing that mammoth calculation to get the features, right? So I was processing something like 100 terabyte data, and it used to take like 15 days to extract the information about users. And but we thought that it won't be useful for others, but as a organization, when you are doing machine learning at scale, this is something that you got to keep in mind. Wonderful, wonderful. And I think this is going very well, and I think we'll make a sequence of this webinar itself as a course. You know, the course will be like a public webinar. I think that's a better idea. What do you say? You are muted. You're on mute.
Completely fine.
Yeah, wonderful. Please, let's just start. There are a couple of questions there before we start. All right. There are a couple of questions. Let me just open the. I'll.
Yeah,
Okay.
so that
So there is one. One question was, what tools do we use for ML model deployment in production environment?
all right. So I think, if you are using TensorFlow or a Keras model, I would expect a stack built on Kubernetes or Kubeflow, right, to be an ideal production deployment scenario because of the notion of pods, auto scaling, wrapping up the right abstractions, right? Uh, like similarly, if you're working with PyTorch, you've got very specific serving containers, like which I would say uh, I would put the containers from this list, right? As in, let me just share. This is I've used some content from this, but this awesome production machine learning is awesome TensorFlow, awesome foobar of the awesome series of GitHub. This is excellent, right? I mean, it goes into everything that we spoke about: explainability, testing, debugging, so on and so forth. It's got the tool, the framework for the language of your choice, for the platform of your choice. So I think, I will start with saying that, if you're working with Keras and TensorFlow, you should be ideally leveraging like the best containerization approach to deploying it in production, and I would
So
go with Kubeflow.
a follow-up question is that what if I'm working with .NET? All right. So I'll take it for right. So first is, how do you deploy the model? One thing is that, so you deploy the model usually like a small microservice independently. Am I right, Venkat? You are also doing that same thing there?
Yes, I mean, as in terms of the thing is, you also have multi-tenancy of multiple models in a single TensorFlow serving container to optimize the throughput. You also, again, the fact is you can pin a GPU and have your CUDA process executing very specific parts of your model. So, what do you mean if you're working with .NET? I mean, the question, I want to know is, what is it in .NET that makes it impossible to use a prediction system? I'm not getting it. What is it about .NET? It's
This
just a
so
regular
see
machine.
the .NET is .NET YOLO V5, right? Their
Yeah.
models actually work pretty well with .NET. And question is, a model trained with .NET, like YOLO v3, YOLO v4, can we load those in TensorFlow? That is the question, I think. Yeah.
See, again, I think the fact is you can load those as the tensor, the weights in the TensorFlow server backend, right? I mean, loading that in your Flask app is not going to pull off anything, right?
Right,
So,
right, right.
and I think that is where the key thing is. I mean, your Flask app doesn't have the, uh, sorry,
So, so what we did when we were deploying the darknet
your
model.
Flask app doesn't have the capabilities that the TensorFlow server or TensorFlow model server is built to deal with servables right now. But like, again, the fact is if your model is humongous and you have a constrained footprint, then you need to think of pruning, quantization, compression, and other facets before you actually deploy your model, right? If you're actually deploying darknet to or YOLO v5 on a very small, mobile footprint device, like you have to think in terms of 8-bit quantization as from starting from scratch, right? As in, you've got to reduce the number of layers, you've got to reduce the number of hyperparameters, and all of those are magnitude reductions, right? So I think that is the way you approach the problem, right? As in, you approach the problem for the hardware or the platform that you're deploying. You don't look at it as like a one size fits all. It's like, you might be able to just deploy if you have a humongous machine with also a massive amount of memory. Yes, you can deploy it on that machine, but you
Right.
cannot deploy it on a $40 AWS EC2 instance, right? So I think that's the key.
Wonderful.
I hope
Wonderful.
that answers the
Yes,
question.
yes. It's a one thing. I just want to add on that. So the way we deployed darknet was using 0MQ and connected it there. Also, the darknet provides the API to make it run there. One of the things that most of the engineers miss out is that creating a neural network in memory, like what does it involve is these numbers are stored, model is nothing but bunch of numbers stored in a file. Your model will read those into the memory. So reading time is there. And then constructing the neural network is another time, it takes a humongous time. As opposed to many people, people believe that in the beginning that, oh, if I just put it in a cache somewhere and then created the neural network after reading from the RAM, it'll certainly make it faster. No, you have to keep your neural network ready because like the amount of time it takes to do the prediction, approximately in almost every case, it took 2x time, twice time to actually load it. Therefore, if you keep it ready in the memory, then you can serve it faster. And the TF-serve, TensorFlow has a wonderful set of libraries. But in certain cases, when I could not get the TensorFlow to work, I ended up using 0MQ or any other service system which keeps it in memory. Like I couldn't do it with Django because it was not keeping things in memory ready because it's a single threaded system. And we had to end up with 0MQ. So those kind of things, I think we will deep dive, and I would also learn to see the perspective of Venkat as we go ahead in this particular sequence of webinars. And we'll move ahead now. Okay, there is one question from one more question. Why do we need Cassandra feature store since for training it's using Hive data store? So I'll explain to you. So Hive is essentially a processing engine. Okay, Hive is essentially like this: that I got this data in HDFS, I write a query. This Hive will convert this query internally to maps and reduces, and it'll run these logic on hundreds of machines near the data. So Hive takes your SQL query, converts it in logic, execute it on hundreds of machines, and then gather this result of the SQL and combine result of the execution from all the machine and combines and processes it and gives you the results. So Hive is not a store per se. Hive actually just stores the data in HDFS. Hive is like an analytics engine. And the truth is that Hive actually itself is using HDFS. So you can, of course, create new tables in Hive, but the data will be in HDFS and the meta store will be here. Now, the other thing is that Hive has a bad, the latency. Latency problems are high when it comes to Hive, because Hive is designed for processing petabytes of data, and it is not designed for fractions of seconds of latency. Therefore, on the other hand, Cassandra is designed for very low latency. It just works very good. And there, what people do is, after processing data using Hive, you structured your data in the form of features. You got, from the logs, we extracted the behavior of users in the form of like parameters, right? How many times this user visits this particular page, how many times this user is actually coming, right, from which country did that. So we extract this information from the logs, which is in terabytes of data, and we created this profile of the user or the product and extracted the feature of the product. And then once we have done that, we basically push it to, say, Cassandra data store, and from there the serving can happen. All right. So yeah, I hope that was useful for you. Please go ahead.
I just wanted to start off again on the training front, right? You know, where we stopped, right? I think is my screen being shared?
Not yet.
Okay.
Now it started. Wonderful.
Perfect. So we mentioned training, right? So one unique aspect of their training system, right, is the training jobs can be configured and managed through a web UI or an API, often via Jupyter Notebook. So that gives the convenience, right, of like, you know, use the API and workflow tools to schedule real jobs. I mean, you can use Postman to set up your training job. I mean, that's amazing, right? As in, so I look at that as providing an API, right? The API facility for training and providing and making the orchestration available through an API empowers teams. Well, then let's actually go to evaluating models, right? As in, I think I'm gonna, you know, that's this, everything there in that world, right? But like, you know, when we talk about evaluating models, I mean, it's not just precision and recall, right? You have many, many nuanced aspects of evaluation. And even though that plot might look humorous, that's depending on the machine learning problem, the metric that you train for or optimize for, or the metric that you consider, will be from will be a very specialized thing. So let me actually take the notion of melanoma or cancer detection, right? As in how many people in the population have cancer, right? So your data set is inherently skewed and imbalanced that way, right? So if you're going to use accuracy, you drop the ball right there. So a problem as nuanced as this, I mean, if you're talking about the data, okay, let's say you have imbalance learn and you use minority oversampling, but that doesn't work for this 99-1 scenario. Rather, what one needs to do is actually both take a step back at the data stage, and from a metric perspective, think of false positive rate at false negative rate equal to 0.1. False positive rate at false negative rate equal to 0.2. Like, you know, you essentially have to train against the objective with the patient in mind, right? And what I mean by that is a cancer patient, if you tell that person they don't have cancer, that is a catastrophic prediction. And your evaluation metrics should be domain specific, right? So accuracy, PRAUC curve, ROC curve, all that, all well and good. F1, not at all good, but when we actually take a step back, your metrics does not fit a cookie cutter pattern. Your metrics are for the problem. So I think the good thing with Michelangelo is they provide like a model accuracy report, like, with again these customized metrics. Now, like, essentially for classification problems, you see they've got like a confusion metric and precision recall ROC, and I've got like, say twiddles to change the index and see where things are like. So, I mean, what I'm trying to, again, like, let's take a look at decision tree visualization. They're actually allowing you to drill down into the decisions made at each node of your decision tree in a certain sense, right? And that is fantastic debuggability, which, like, I would say is a well thought out engineering decision. And the other aspect, right? It's not just the performance on your test data or validation set that you're concerned about. I mean, you also have to look at how your features behave, right? So they've got to actually show the distribution, the shift over time, and that allows one to, like I said, like go and when you want to debug if the feature has changed over time, what has changed over time, right? So you providing snapshot of the model, snapshots of the features, snapshots of the data allows you to do any sort of debugging on these three indices, which is important to mention. And let's now consider deployment, right? As in, well, you've got offline deployment, like the offline container, Spark job to generate batch predictions either on demand or on a repeating schedule. You've got the online deployment scenario where, like, online prediction service cluster, hundreds of machines behind a load balancer. The microservices philosophy might be leveraged, and clients can either send individual or batched prediction requests as network application calls, right? So again, I think the key thing is the microservices philosophy. Why is like separation of concerns is again there, right? As in, like, you don't want to have a giant monolithic model serving all your features, all your models, or giant monolithic system being a spaghetti that serves everything. How do you debug what went wrong where? Which model is actually responsible for causing the performance problems? Which model actually took down your server, right? So Abhinav has a question. Does Google have any open source alternative to Michelangelo? Yes, and it's called TFX. The TFX platform is available, and I think, if you could just search for TFX, you can. They pretty much provide all of this. It's in my interest not to talk about Google technology since I work for Google, so I think it's best that I stuck to Google. So let's go with the make prediction scenario, right? Like, finally, we've come to a stage where we've got either the batch mode or the real mode making predictions, sending to either Hive or Kafka in the stage, right? And well, I think the key thing when you make predictions, and I'm sorry, I think yes, when you make predictions is the notion of explainability, debuggability, and, like, saving a certain fraction of your predictions for analysis later, right, is a pattern that I would recommend for hygiene, right? And again, like, when you make predictions, machine learning systems run in a feedback loop with the world. The prediction from the world comes back to the system, right? So in a sense, like, the data and the system are in a cyclic loop learning from each other, right? So hence, that is why your predictions need to be stored in a certain sense for you to, learn that cyclically.
Yeah.
And
Can I
yes,
add something?
yes,
So
please.
another thing is that when we are, let's say, building something. So let's say we are building the place recommendation, or we'll building a video recommendation service. So what happens is that there are certain users who we do not know about. So we call that cold start problem. We do not have any information about the user. Therefore, we cannot really give them the prediction based on the machine learning model usually. So what we do in those cases is that called cold start. We keep the predictions ready for the anonymous users based on the location and other characteristics. So for that, what we do is instead of this way, what we do is we basically prepare the pre-prepared recommendations or things like that and sift it. And that's where that I think predictions you're talking about that we push it to Hive and Kafka so that it can be used right as a result. So that cold start problem and so usually your in production time you will have two form of predictions. One is something like we take it from the database and give it to the user. That is static predictions, right? If the user we have no clue about the user. Second would be the predictions done by the model, which looks at the user's characteristics and tells that this guy will like this thing. So those things would be delivered by the service as okay. Go ahead. You are on mute. Wonderful set of questions. I'm enjoying the questions in this discussion. Go ahead, Venkat, you are on mute. Yeah.
All right. So I think one like thing which I'm going to talk about like with the production scenario is like when you make predictions, you often also need to store the metadata associated with the model that made the prediction, so that like for your A/B experiments, right? So I think this is important that you store some sort of a UUID for the model, have that the signature characteristics, so that you annotate the prediction with enough debugging information. When a production failure happens, you can actually go back to which model and what its associated features were that allow you to debug.
Perfect.
The
So
last
before
monitoring, I'm going to just talk about monitoring very briefly, right? So
yeah, yeah.
essentially, if you're familiar with Prometheus and Grafana, or like any monitoring system, what do you need to monitor for machine learning jobs, right? As in, apart from throughput characteristics, right? Number of image classifications made per second, the 90th, 95th median latency of classifications. But I also think it's very important for you to monitor number of anomalous predictions, number of datas, like where the bad data, the rotten eggs, the breaking bad, right? As in you're constantly seeing bad input. So that also, in a certain sense, like when you fail a prediction or when there's something catastrophic, it is very important to log that and to keep a record of that for you to actually go. So thank you, and
I
with
just
that, I end my part.
there are so many wonderful questions that people are asking. One of the question is ML faces huge problem, namely that individual developers tend to overload themselves. In real life, there are DevOps and there are the domain experts who design the models. All right, this is one of my favorite questions, and I'm going to answer this. All right, so when I joined this company in the beginning, that was my first assignment on machine learning, right? There was this, there were these DevOps engineers, and they were wonderful engineers. I'm not saying that. And then there were researchers, and there was me, who was a technology lead, and I was responsible for overall deployment. Now, what happened was that the data scientist worked on this system alongside. I basically sat with him and all of that. He's just wonderful guy. And when I went to deploy it, we realized that problem I talked about, that 4 GB RAM problem. Okay. And DevOps guys, they said that that's a rule. We can't do anything about it. The machine learning scientist said that I have done my job, created this great model. Now, who can I give the excuse to? And that's a true life of a software engineer. So you are sandwiched between the two extremes. They both said that it is not my job, right? And the rule was simple. So at this point of time, the only thing I was left with is just go through the model and understand why does it require that much memory, and why does it. So I started realizing it, and we did the reverse engineering entire thing and figured out that we can, instead of loading everything into a hash map, I can actually do it using a disk, right? Sort the data using disk and serve it from the disk quickly. And serve it from the disk in the sense that we can just keep a small footprint in the memory. So the truth is that I started with that psychology that let the experts do their job, but the life is not that beautiful. At the end of the day, software engineers need to understand DevOps. They need to understand big data. They need to understand the machine learning. Okay, and that's the truth about it. If you take a look at the interviews that Facebook, Google, Uber, anybody today is doing, right? So they have these coding rounds, they have the design round, they have the machine learning round for the same engineer. So this engineer who is being hired at a, let's say, little senior level, machine learning engineer, they call it, he's expected to know the big data problems. He's expected to know the machine learning one. He's expected to know the software engineering and of course the DevOps. That's why, and the truth, that's the truth. Like if you see this diagram that Venkat is displaying on his machine right now, this one has everything in it. There are DevOps, there is a real-time data processing, there's a big data processing, there is a ETL, there is uh, I mean machine learning, there is DevOps, everything is there. So that's the important part. So as a senior engineer, you got to know everything because you are the dots connecting the various people. And that's the reason why we decided on this particular course, the scalable machine learning. The idea is that to design a software, you need many things, and therefore you need to know many things. And today's time, that has become very difficult. Like when I meet engineers, some say that, oh, I'm just a web developer. Some say that I am a mobile developer. Some say I'm a DevOps guy. I'm an analytics guy. I'm a machine learning guy. But the truth is that when you go to a company, you will have to be the one-man army at times. And you will have to at least understand everything. And that's exactly the sole reason behind this course. This course is an intersection of DevOps, machine learning, and big data engineering. And this is that's one of the reasons why I feel this course is so important to me, because I've seen so many projects failing just because of lack of this kind of engineers who know it all. And most of the top companies realized it, and therefore they changed their hiring strategy to include a person. And I have been, a number of people actually come to me asking for people who can do everything rather than only one thing. And there's a huge demand of it. So I would say that being a software engineer, Do not bucket yourself into one thing. Know everything. Knowing something has more advantage over not knowing something. Okay. So it's not like if you learned machine learning being in a DevOps, you will not get a job, right? So, or if you are in machine learning, you learn DevOps, suddenly you'll not get machine learning job. No, you are becoming more and more powerful. And that's what is happening. As Elon Musk says, that we are not reptile, we can be everybody. Okay. And right, that's how it is. So my suggestion to everybody will be that be open-minded when it comes to technology, tend to learn more and more things. If and this course, the one that we talked to today, we're going to go slow in future. This was our introductory session just to get you an idea as what is expected out of an engineer, what is not expected, what are the things you have to take care of. And this today's session basically sets the idea about what we are going to talk about in the future courses. So in the future webinars of scalable machine learning, we're going to take individual parts and go a little slower, right? The idea is that you'll take a simple model, build it, deploy it, optimize it, then optimize at scale, and we will continue to make it more and more practical and realistic. And that's the idea that we're going to go with the scalable machine learning webinar series. All right. I
Let
hope.
me just say a practical aspect. We will take your fashionist and take it from few predictions per second to thousands of predictions per second, right? All on the same this thing, and show you that
Exactly.
path and explainly.
Wonderful.
I'm going to take the next question by Ujay Chandran. Is the scalability influence when the model faces data that falls under different types, numerical, categorical? Let me actually take this. It's about the size of the tensor, right? As in text is not expensive to tokenize or process, but like, if you are considering images, where you have to take a large image, assume that's in sent over the network, and that's a humongous JPEG image, right? As in it's in megabytes, and you've got to convert it into a four-dimensional tensor, 224 XXXC number of channels, width, height, this thing, and then that is a very expensive operation. So the pre-processing step for images are costly. Videos are costlier. Audios have 10 million time sequences. So with videos and audios, compression comes in, right? So even with images, compression comes in. You might probably compress and send it over the wire. So I think there's many facets to data, right? Categorical data, I mean, that's like converting a feature and making it categorical is two magnitudes lower than converting an image to a tensor. So I think that's the perspective that one needs to have.
Wonderful. Wonderful. So yes. And another question from Ravi is, of course, one more thing I would like to add to your answer is that if the data is a video feed, right, or a music or audio, then that complexity adds on further, as described by Venkat, right? So great. Um, a question from Ravi is it like displaying popular and featured product in e-commerce website for the first time users? Yes, that's cold start, right? That's cold start. I think that was the question regarding cold start. Yes. So if let's say there's a user and our model is not trained to predict, or we do not have that much predictions or that much suggestion for a new user, what we generally do is we create something called anonymous user. Anonymous user does not have certain features. It has certain other features like the location, the browser they are using, the time, the day, and so on. So sometimes cold start problem where we don't have information about the user is solved by making a user persona based on the generic characteristics such as time of the day, location, as in the country, and right, and those kind of characteristics, or on which page is this person right now. So those are the few things, and let's move ahead. Another question is how we can secure our model either in dev, staging, or in deploy environment. You want to take it, Venkat?
Yes, please. I think this is a great question. Thank you, Hajlo Jaladin, for a fantastic question. I think so. This is where the notion of model versioning, right? The UUID aspect, the signature, right? So the A B, or having two different versions of your model, right? As in, I'm going to use the canary in a coal mine analogy, right? As in, when the olden days, coal miners used to take a canary to see if it's safe enough for them to actually go into the coal mine. And we call the process of canarying, right? Where we bake a model, give some traffic to it, like a little bit of traffic, right? Before we really push it to 100%, right? So I think the notion is any time that you push a new model, you need to play it safe, you need to play it slow. And I actually, my word goes for traffic-based updates, right? Where you start with 1% of the flow getting the new model, and then you have enough confidence, then 5, 10, and then okay, the new model works, there's no feature drifts, there's no bad data problems. And once you're fully confident about that, you basically push it all the way to 100%, right? So this notion of blue-green testing, or A/B testing, or canarying, right, is a fairly common practice in production deployment, but in machine learning, the frameworks, maybe TFX provides this out of the box, right? But in most cases, right, if you're in a colab pipeline, all you're just going to do is export the model to the same directory, and that's it, done, right? The latest timestamp is picked up, and you have no idea what went wrong where. So this is an excellent question. I hope I answered this.
Wonderful, wonderful. So, our question is, do you have separate training for Kubernetes? We have a DevOps course. It's a wonderful course designed by my co-founder, and he's wonderful when it comes to the deep dive understanding. And so, please take a look at the DevOps course. You would really like it, right? I personally have also gone through the course. So it is on the main website of CloudxLab, and take a look at that. Or, if you do not have time for the training and the course, but I'll just give you a brief that this course covers everything about DevOps, starting from starting from even Git. It starts from Git and keep on moving to the Kubernetes and Docker and so on. And if you do not have time, you can just go to Kubernetes website and you can just go through their tutorials. And question is, this webinar is available in Zoom. So this webinar, we are going to keep it on YouTube, just like in this format. This webinar series on scalable machine learning will be available on YouTube live, just like today. And you can ask questions in the same way. All right. The Zoom one, we are going to keep it only for panelists. And there would be multiple panelists who would basically we'll keep this class more of a discussion than, one-way traffic. Okay. Question is, what is stream engine? Do you want to take it or should I?
Please go ahead, Sandeep.
Okay, so basically the stream engine, if you think about it, the stream engine is something that when you think about data coming in from the user continuously, right? People are essentially, let's say, how should I say? Some orders are being placed on your website and there are multiple things happening and you want to display the aggregated values right? So those kind of things you could do using a stream engine. A stream engine is essentially what it does is it breaks down the continuous flowing data into windows and it runs the logic on top of it. Okay, like it could be saving that into a disk, it could be converting those that window of packets that is coming in into something like a tabular data and so on, or converting that into features and so on. So that's essentially the stream engine. Okay, Venkat, do you want to add anything to it?
No, I think you answered it succinctly.
Okay. Perfect. I think, and please stay tuned to our channel, and we will be coming up with more. Today's session was really heavyweight, even for me. And what we're going to do is, yes, it is just too many things. So what we're going to do is, from next session onwards, we're going to make it start from the scratch and build it slowly, and then make it complex in the sense like increase the complexity and increase the latency need and the number of users, and those kind of designs are something that would help you think about large scale and so on. So in case you are new to machine learning, do attend to the machine learning course that is starting now. You can do both the things parallelly, this webinar series and the machine learning course. And there is this wonderful machine learning course we just started. It's going to start from the machine learning, go to the big data, and also the deep learning. And this is going to cover the theoretical as well as the practical foundation of machine learning and deep learning. So for this particular webinar series, we expect that you know basics of machine learning. You also know basics of big data architectures, and you also have a basic idea about the DevOps tools. Okay. But having said that, we would try to keep things very rudimentary. And I would suggest that take a look at the courses at CloudxLab on all the three parts. All the audience who started the session, they stayed till the end. That's a unique thing that has happened in these sessions. And I look forward to see you in the future webinar. Stay tuned to the YouTube channel and do subscribe to CloudxLab. And you can just start with projects. I would suggest something. There are free projects. You can just start doing that, and there are like tons of resources at CloudxLab. If you go to CloudxLab and click on resources, you'll find tons of things that you would like to do and experiment. And what today we have discussed is the real engineering. And this real engineering is what is the need of almost every large company today. Thank you, everyone.
Thank you, Sandeep. Thank you, everyone.
Bye.
Glad to have you all. Bye-bye.
Large company today. Thank you, everyone.
Thank you, Sandeep. Thank you, everyone. Glad to have you all. Bye-bye.
Hello, everyone. Please stay back for 2 more minutes. We have some explaining to do. So, as you can see on the screen, we have launched our Artificial Intelligence and Deep Learning course from IIT Roorkee, and the registration for the same has almost come to an end. The last date for application is 28th June, so kindly apply at the earliest as it's on a first come and first serve basis. We have also issued a coupon code for the users of the webinar. So the coupon code is valid for 6 hours from now. It is valid on courses from CloudxLab directly and not the ones with the collaboration from IIT Roorkee. So, guys, please do use this opportunity to begin your journey to upskill in the domain of your choice. So, once again, thank you everyone for attending the webinar. Have a good night. Stay safe. Bye bye.
Thank you, everyone.
Thank you, Sandeep. Thank you, everyone. Glad to have you.
Hello, everyone. Please stay back for 2 more minutes. We have some explaining to do. So, as you can see on the screen, we have launched our artificial intelligence and deep learning course from IIT Roorkee, and the registration for the same has almost come to an end. The last date for application is 28th June. So kindly apply at the earliest as it's on a first come and first serve basis. We have also issued a coupon code for the users of the webinar. So the coupon code is valid for 6 hours from now. It is valid on courses from CloudxLab directly and not the ones with the collaboration from IIT Roorkee. So guys, please do use this opportunity to begin your journey to upskill in the domain of your choice. So once again, thank you everyone for attending the webinar. Have a good night. Stay safe. Bye bye.